Ludwig Boltzmann and the Revolution of Entropy. Everyone knows what happens when ice is added to hot coffee, right? The ice melts and the coffee gradually cools. But have there ever been times when the ice became even colder and the coffee started boiling? Of course, that never happens. Why? During the Industrial Revolution in the 18th century, the steam engine appeared. People began to ask, how can heat be converted into work most efficiently? As they searched for the answer, a new field called thermodynamics developed. French scientist Sadi Carnot studied the ideal steam engine and discovered that heat can do work only when it moves from a higher temperature to a lower temperature. But no matter how efficient an engine is, it cannot convert 100% of heat into work. Some of the heat must always flow elsewhere. Why is this so? First, because of the law of conservation of energy. Energy does not appear or disappear. It only changes from one form to another. If all incoming heat could be converted into work, it would be possible to build a perpetual motion machine that runs forever. But this is impossible in reality. This is exactly what the law of increasing entropy, known as the second law of thermodynamics, explains. Think about an iced Americano. Heat from the hot espresso flows into the ice, melts it, and cools the coffee. But what if the heat flowed from the ice into the coffee instead? The ice would become even colder, and the coffee would become even hotter. But this never happens in nature. Heat always flows from a higher temperature to a lower temperature. German scientist Rudolf Clausius explained this natural direction with the idea of entropy. Entropy is often described as the degree of disorder. Entropy increases as heat spreads out instead of staying in one place. That is why nature gradually changes from an ordered state to a more disordered state. Then one question comes to mind. Why does nature always move only in the direction where entropy increases? The person who offered a new answer to this question was Ludwig Boltzmann. Boltzmann focused on the fact that a gas consists of countless molecules. Calculating each molecule one by one is almost impossible. But he believed that looking at the whole system through probability and statistics could reveal patterns. For example, it is difficult to predict how one student will move in a classroom, but it is easy to expect that most students will come out into the hallway during recess. Boltzmann believed that molecules behave in a similar way. He statistically calculated the state that molecules are most likely to occupy, and found that the direction in which entropy increases is the most probable state. The second law of thermodynamics was not an absolute command, but nature's most probable choice. Boltzmann's research became the starting point of a new field called statistical mechanics. Thanks to his work, people can explain the motion of countless invisible molecules with probability and statistics, and understand the changes in heat and energy that we encounter in everyday life. The next time ice melts and turns into a refreshing cup of coffee, take a moment to think about it. Even in that ordinary event, countless molecules, probability, and the remarkable order created by mathematics are quietly at work.